The title of my speech is Fatigue Assessment by Inertia Approach during tensile and fatigue test on PPGF35. For this work, tensile test and fatigue test were carried out with the hydraulic testing machine, and during all the tests we use the AC and air camera to measure the surface temperature, to detect the surface temperature evolution during all the tests, the tensile and the fatigue test. The aim of our study is to apply a thermographic method presented by La Rosa and Risitano 17 years ago for the fatigue assessment of this material, and taking into account that the composites have a different behavior to more complex fatigue mechanism with respect to the metals materials. These materials are used for structural components like bearing gears for the lower cost, and the failure is normally a fatigue failure. During a static test, you can see with the red curve the surface temperature evolution, and you have three stages. The first stage is the thermoelastic equation that you see is a linear degree of the surface temperature. The second, you have evolution of the temperature, a deviation from the linearity, and after the third, you have a high increment of the surface temperature until the failure. For the first time, Clienti et al. In 2010 correlate the deviation from the linearity, it's the end of the phase 1, with the fatigue trend of the plastic material. A little short summary of the thermographic method. If you have fatigue test under fatigue limits, and then you have a air camera to detect the surface temperature, if you are under the fatigue limit, you see the red curve. You have no variation of the surface temperature. But if you are over the fatigue limit, you can see three stages of the temperature. One is an initial rapid increment of the temperature. A second stage, very big, where you have a plateau and you have a temperature stabilization. And after, until the failure, you have the third phase where you have a new height temperature increment. The area phi, diameter phi, is correlated with the energy of the material. And if you have the temperature stabilization of the second phase, you can predict the fatigue limit. Now, Handa in 2011 see that for this material, for short field fiber reinforced polymer material, you have the phase 1 and the phase 3 similar to metal material, but the second phase is different because you have an increment but a lower slope. The material used in this study is a glass fiber reinforced polypropylene. This is a mechanical parameter, and the specimen were injection molded with this parameter. This is the shape, and this is the geometry, the dimension of our shape. The site tests were carried out on a servo-hydraulic Ital Sigma machine at a cross rate of 5 millimeters minutes and on 15 specimens. During the test, we use the IC technique and a FLIR camera. The fatigue test was carried out on another set of 15 specimens with load ratio of minus 0.1 and a frequency test of 5 Hz. During all the tests, we use the similar ER camera. The humidity and temperature in the lab are constant, and the temperature are 23 Celsius and humidity 50%. Two types of tests were performed for fatigue test. One series for 11 specimens with the constant load, and for 4 specimens we carry out with the increment load step. In this slide you can see the stress strain curve, and this is some picture about the DAC, and you can see the strain of the specimen during all the tests. For all the tests, the behavior is similar. Okay, this is an interesting slide. In blue you have the stress curve vs the time, and in green square you can see the surface temperature variation detected by the camera. The red circle are the theoretical temperature variation by the thermoelastic equation, by these parameters. If you see the black line is the deviation from experimental temperature variation from theoretical temperature variation, you can see that is a difference for a stress about 56 megapascal. Remember these values. During the fatigue test, you can see the HANDA behavior. We have the initial rapid linear increment of the surface temperature. You have another linear increment with lower slope, and until the failure, you see a rapid increment. This is the SN curve obtained by the traditional method, and it's very interesting to see that you can see the fatigue limit is between 52 and 57 megapascal. If you use the thermographic method with the surface temperature of the phase tube, you can see a fatigue limit of 54 megapascal. In summary, we can see that with the traditional approach, we have this value of fatigue limit. For the thermographic method, the classical thermographic method during fatigue test, we have this value, and after, with the new thermographic static method, you can see this value. In conclusion, we use a full field technique for the strain field, and a full field technique for the temperature of the specimen, and we can see that there is a good agreement with the experimental value, with the thermographic method, a classic thermographic method, with the new approach we propose, and with the classical method to have the fatigue limit. Thank you for your kind attention.
We have time for only one question. If not, okay. Thank you.